Okay, so we're looking at problems from 1.2. We got a quiz on that tomorrow. Starting with number 9.
A 46-gram piece of ice at 0 degrees Celsius is put into 139 milliliters.
Well, hold on. In 139 milliliters
of 60 degrees Celsius water in an insulated cup. Does all the ice melt? What is the final temperature when everything is at equilibrium? And how much ice is left when everything is in thermal equilibrium?
So, we got 2 questions. Now, conceptually, what's one of these going to be?
0.
One of them is going to be 0. Which one?
The ice.
We don't know yet, right? Well, maybe you've done enough work that you know which one is going to be 0.
I went to another office hours.
I know.
For hours.
Yeah. So we know one of them is going to be 0. The question becomes, which one is going to be 0? How do we know which one's going to be 0? And how do we deal with it from there? So we look at this and we say, okay, how can I tell which one is going to be 0? And really, this is something we did in class as well. We have to do this consideration of which one has more energy. The maximum energy my H2O could lose is from 60 degrees all the way down to 0. Otherwise, it's going to be turning it into solid. And I should call this H2O liquid because H2O solid ice is still water. It's still H2O. So we're going all the way to 0 degrees Celsius, and I'm going to compare that to the energy needed to melt all of the ice. I'm just going to compare, see which one is bigger. So this is going to be a Q is equal to MC delta T. Our mass is going to be the 139. Our C is going to be 4.184. Our delta T is going to be 60 minus 0.
Isn't it 0 minus 60?
It is. You are right. Final minus initial. Thank you. 0 minus 60. Plus, we should be putting, this should be losing energy, so I probably would have caught it when I got a positive Q here. I would have scratched my head and said, wait, why is my system cooling off, gaining energy? But it should be an exothermic system. Good catch. Okay, so then we just plug in those numbers and say how much energy. So do 139, oops, missed my 3, 139 times 4.184 times 60 negative. So this is going to be 34894 joules. Right, so there's a certain amount of energy. My water at 60 degrees, if it was in contact with a system at 0 degrees and lost all of its energy, all of its kinetic energy, all of its temperature energy, all of its heat, it would lose 34 kilojoules, almost 35 kilojoules of energy. Right, and then I say, okay, well, how much energy? Come on in, grab a chair. If we tuck bags underneath desks and things, it'll make more space for people. You can take this chair. Then we say, okay, how much energy does it take? I'm also recording, but it's just a word. How much energy does it take to melt all of my ice? Is this enough energy? Is this not enough energy? How much does it take? So we look at that, and if we're melting ice, it should be positive. And which equation do I use?
Mass, moles times H plus.
N delta H, right? This is a phase change, so we use our phase change equation. We'll call this Q1 and Q2. This is going to be N delta H. I'm going to do my mass of ice of 46 grams divided by the molecular weight of H2O times the delta H for ice, which I happen to know the enthalpy of fusion for ice is 6.01 kilojoules. I'm going to go ahead and just turn that into 6010, so it's joules per mole. And I'm going to get an energy associated with that. The question is, which is bigger, which is smaller? So I'm going to do 46 divided by 18 times 6010. Oh, and that's going to be 15358.8 joules. So about 15 kilojoules of energy. So does all the ice melt? Yes. What mass of ice is left at equilibrium? 0. Right? There's no ice left. The problem is, what's our final temperature? And there's a couple different ways we can go at this point. So keep these two numbers in mind. They're going to come back, but I'm going to set it up a different conceptual way to think about it. Right? Because we could do this mathematical thing where I essentially say whatever energy is left over goes into heating up the water up from 0, and that would work. But that's not what nature does. So while that's calculationally reasonable, it's conceptually unreasonable to think that water is going to go down to 0 and then warm back up. It's not, nature doesn't do that. Right? Throw ice into a cup, it's not like, right? We're going to hit an equilibrium, so it's going to essentially approach a final temperature. Again, I'm going to write these numbers in the corner real quick because you'll see them come back. -34894. We'll call that Q1. And actually, that number is not going to come back. It's fine though. And then we're going to have 15358 Q2. And we'll see which one of those comes back. So I'm going to erase this work in blue. And we're going to look at it kind of conceptually what happens as our ice melts into our water completely. We ready for that? Okay. So, now what happens, I'm going to switch colors to be dramatic. Now that I know, hey, how's it going? Now that I know, yes, all of the ice melts, I can say, okay, well, where does that leave me? Well, I know that I'm going to have some total energy. I'm going to have, like, the Q of the ice melting. And it's going to get that energy of melting from the Q of the water cooling. That ice was already at 0 degrees, and so when it melts, it's going to make a 46-gram blob of water at 0 degrees. If that water is in contact with this warmer water, now the water bath doesn't get all the way to 0 degrees to make that happen. We see the difference in the energies. So where does the other energy go?
Heating up the other water.
To heating up the melted water. So I'm going to have another Q over here. I'm going to call it something weird. I'm going to call it ice melt warm. Right? So I'm going to have some amount of energy that goes into melting the ice, and then whatever energy is left over is going to go into that melt warming up. And so really what we've got here is we've got our typical Q in and our Q out, equal and opposite to each other. Don't forget your negative sign that I almost forgot in writing down all my Q's. Right, they're going to be equal and opposite to each other. And again, I like to make my Q out negative so I can get rid of my negative signs early. We don't need to worry about work in this case. There was a question before I started recording about work. Right, in this situation, yes, the volume of ice to water is going to change. There's going to be a delta V there. But that delta V is going to be really small compared to these kilojoule values. And so we can ignore the work in this case. Even though there is a volume change, we're doing this at constant pressure, but there is a volume change. So, but it's a small volume change. The amount of energy associated with the volume change is going to be on the order of 10 joules, whereas we're on the kilojoule scale. So we're just going to be like, hey, let's just ignore that work term for now because we don't want to have to keep track of the volume on top of this. And especially if we're doing it in an open container where there's no pressurization, that it's going to be like a small term. So we can ignore that and we can just focus on the heat energy. So in this case, Q is equal to delta H is equal to E, delta E, right? We're ignoring the P delta V term. So in that case, we can just say cool, okay, I'm going to start throwing in my equations. Now, the ice melting, we already did this. This is going to be that N delta H. And that's going to have the same value we had before for Q2. This one is not going to be the same as Q1. It's not going to be the same. Because in this situation, we're going to have that MC, I'm going to go ahead and write T final minus 60. T final is not going to be 0. It's going to be something greater than 0. It's got to be something greater than 0. So we can try to figure out, well, how much higher than 0? That's the whole point of what we're trying to figure out. What do I put for this one? Same thing, right? This is also going to be an MC delta T. Well, let me plug in my delta T terms, right? T final minus T initial. T final, still not known. T initial in this case is 0. These things are equal and opposite to each other. The other thing we have to be careful about is defining my ice system versus my surrounding water bath system, so I don't get my masses mixed up. Right? So I don't need this water to warm up at all. This water is going to be the 139 milliliters, which density turns to grams, times my 4.184 joules, grams, degrees Celsius, T final minus 60 degrees Celsius. Right? That's that side. This side, N delta H, is going to be the same numbers we had before. Right? And this is my ice side. This is my surrounding and system. Assuming that we're in a really nice insulated system, I don't have to worry about losing energy to the room or to the cup or to the air above it, right? We're in a nice, closed, compact system. Everything's blocked in. As long as we're quick. And if we take too long, of course, your coffee still gets cold because it's not perfectly isolated. But again, approximation land, we can say, look, we put it in a styrofoam, we put it in 2 styrofoam cups with a piece of cardboard on top. It's completely isolated from the rest of the universe for us. Right? So in this case, my N delta H is still going to be that 46 divided by 18 of 6010. Yeah, there's another foldy chair back there, or you can take this chair, but you know, he also likes to stand. The other thing we have to be careful about, my MC here, this is not going to be the mass of the entire system. It's not going to be the mass of my surrounding water. It's going to be the mass of
Melted water.
the melted water, the ice that melted. So that's going to be 46 grams. Which C do I use in this case? It's not ice, it's water, so we use the 4.184. This is one of the things that really confused people, at least last week, when we are dealing with our ice system, but it's a melted ice system, we lose track as to whether we're talking about the ice or the water, and what phase is it in. We're warming, that's why I call it ice melt, which is just a fancy way of saying water. So I called it ice melt to make sure we're still talking about the ice, but the melt to let us know we're talking about water. Times T final, add that together. Now we're just doing algebra, right? So we had to do, but like, and I know you all can do algebra, so we have to be careful about the conceptual things we're dealing with here, right? We started out by answering the question, does all of the ice melt or not? We just compared how much energy could my water lose, how much energy does my ice need. We saw that the water had more energy than the ice needed at its maximum. So we say, okay, the water's not going to lose all of that energy. It's going to come to thermal equilibrium between that blob of melted ice and the water bath. And so instead of trying to do something that would work mathematically and thermodynamically of like finding the excess energy and then warming up the system to its final temperature, conceptually, mathematically works, but loses track of physical reality. We want to make sure the work we're doing is grounded in that physical reality. Everything we do, one of the things that makes me like chemistry more than math, sorry math folks, is every calculation we do can be rooted in some experience we have of like cooling off a hot cup of coffee. Right? 60 degrees is pretty hot. Like cooling off a cup of coffee by throwing some ice in it. Right? How much ice? What if I wanted to make iced coffee? Well, I just increase the amount of ice until there's ice left over. Now my coffee is at approximately 0 degrees Celsius. It's like iced. You know, thinking about all of those things. And we want to get that kind of conceptual, like, related to physical reality. Let's still run through the algebra to make sure we can do it. I'm just going to plug some things in here. 46 times 4.184 gets us 192.5 T final. Plus, you'll notice we get the same number here we had before, 46 divided by 18 times 6010 is equal to, same number we had before, 15358. I should probably round that to 15359 because there was a 0.8 at the end, but this will be close enough. And then I'm going to go ahead and multiply this through as well. 139 times 4.184 gives me 581. I'm actually going to do, no, we'll leave it as TF. 581, oops, I did 18 instead of 81, my apologies. 581.5 TF. Ah, what else did I forget?
The negative.
I forgot my negative. Let's get that negative in there. And I knew as soon as I went to FOIL it, I was like, wait, that should be positive. Right, because I knew that negative and that negative should multiply together plus, oh, that number does come through, right? So that's going to be my total amount of energy, 34894. So notice my total energy does come back when I multiply this all out. So there's my total energy water could lose. This is my energy that the ice needs to melt. I'm going to do some differences in moving things around. So that kind of conceptual idea we did of excess energy could come back. I find I mostly get confused if I detach my math from the physical reality. So I always try to make sure I'm rooting it in physical reality. Both still work, right? Still just doing math, but I like to have my math rooted in physical reality. I'm going to add this 518 over. I'm going to subtract this 15 over, that 15 kilojoules over, and I'm going to get some answer for my T final. And well, before I calculate T final, let's just do that. 1348. So we'll do 192.5 plus 5, not 18, 81.5 gets us 774 T final is equal to 34894 minus 15358 9536. I didn't do a good job keeping track of my units. If I multiply this all through, this should be in joules per degree Celsius, right? Let me double check this. This number is just in joules. Oh, units. This is in joules. This, oh, it's the T final has the degrees Celsius in it. Okay, because this is going to be, okay. So it's this number has the units in it. So this is going to be like joules, and I'm going to divide by joules per Celsius. Joules is going to cancel out, leave me with Celsius. Let me put my units in there. So this is going to be joules. This 7748 is the weird number, right? Because I've got the grams cancels out. So this is 774 joules degrees Celsius. So now when I divide by the 774, joules cancels, I'm just left with Celsius. Before I do this calculation, things we can, like, physical world tell about the temperature. What are reasonable values for it?
Positive and less than 60.
Positive and less than 60. Can't be below 0 because that's as cold as it can get. Can't be above 60 because that was as hot as it could get. It has to be somewhere between those two. I'm not even going to throw an eyeball guess at it. I'm just going to calculate it. But we know it has to be someplace in that range. Otherwise, we're making nonsense answers. If we ever get a negative, like, now, if the ice was below 0, we get a lot of extra Q terms in here, and we can get lower temperatures. But in this case, we look at our total, our highest temperature, our lowest temperature. We know we have to be in that range when we reach equilibrium. So I take my 19,536 divided by 774. 25.2 Celsius. So we can cool off our water. Now, in order to do this, notice we had to do some careful, like there were things we had to be careful about. We had to figure out does all the ice melt or not. And once we figured that out, we had to be careful about defining our system and surrounding. That's the thing that a lot of people have trouble with because you usually don't get to pick, but we're at a point now where you kind of get to pick. What's my system, what's my surroundings? Do we want to include the cup and the heat capacity of styrofoam? Do you want to take the air gap above the water into account because all of that stuff is going to be in thermal equilibrium with it? Or can we just say it's the water and the ice, all of those things are small variations to it, right? It might drop it instead of 25.2, maybe it's 25.1 if I take the cups and the air into account. Do I need to care about that or not? In this class where it's just a Gen Chem class, like 0.1 degrees plus minus 0.1 degrees, 0.2 plus or minus a degree, probably fine. If we were in some upper division class where we want to be really careful, we might be down to like a 10th or a 100th of a degree we care about. Gen Chem class, close enough. Questions about that one? I went through that one pretty quick. I get a lot of questions about these, and these are mathematically not terribly difficult. There's a couple algebra mistakes that people make, like forgetting the negative, not foiling correctly, forgetting unit conversion. But these actually have a lot of conceptual work in them. And if you're not doing the conceptual work to do this, it's really easy to get mixed up. Questions about this one?
I have a semi-related question.
Sure.
I just thought it feels wrong that it takes the same energy to go from like 97 to 100 degrees as it is from 2 to 5 degrees for water.
97 to 100 to 2 to 5.
Yeah, because it's a 3-degree difference.
Yes. No, it totally does. Now, approximately, right? You can make arguments about how the density of water changes and all of those things, but heat capacity of water is pretty consistent. It does have some variations as temperature changes, mostly negligible for the amount of energy we're talking about, right? So if you calculate the amount of energy it takes to do a 3-degree change, how much water are we talking about? 100 grams?
100 grams.
Sure. So we've got 100 grams of water. That's going to take about 1.2 kilojoules of energy, whether you're going 2 to 5 or 97 to 100. Now, the place where you have some variation, you might see a change in that. Like the density of water is technically different at those two different, but we've got grams already, so if it was milliliters, it might be different. Yeah, but no, it takes the same amount.
There's not like the heat, specific heat capacity doesn't like alter anyway as you like approach the edge.
Whatever your initial velocity was.
Now, the thing that I think is interesting, so the thing that makes it, so I'm thinking about this kind of like in an experiential way. Like on paper, mathematically, yeah, take the exact same amount. Any variations in heat capacity small. The place where like I'm intellectually running into the same kind of like stop to you is if we had water at 2 degrees Celsius in this room, it would just steal an energy from the environment, get to 5 without me doing anything. But if I had a thing of water at 97 degrees, it wouldn't heat up. I'd have to put extra energy into it from someplace. So in order to make this conceptually interesting, we have to be in a room that's at 2 degrees Celsius. And then in a room that's at 97 degrees Celsius, right? So the room is at thermal equilibrium with that water, so we're not getting extra energy leaking in, right? We're able to isolate our system at those temperatures. And that's where in my head I could see, it seems like it would take more energy to get from 97 to 100 than 2 to 5, because the 97 to 100, I have to provide all of that energy. Like, it's not stealing any energy from the environment. But 2 to 5, it's usually stealing energy from the environment in addition to me warming it. And so it doesn't seem like it takes as much. But that's because it's getting that environmental energy. I think that's what throws it off in my mind. I don't know if that makes sense to you as well.
That's probably where the intuition is like.
Yeah, so the intuition doesn't match with the kind of the numbers on the paper. It's because our intuition is usually operating at 20 degrees Celsius, not at 97 degrees Celsius or 2 degrees Celsius. And if our intuition is operating at 20 degrees Celsius, the 2 is just going to naturally get to 5 on its way up to 20. The 97 will never get up to 100, intuitively.
Yeah.
And so it feels like we have to put energy in to get those 3 degrees.
I guess the other part would be uncertainty and what really happens at the phase change, like as it
Right,
starts
so-
to break the ion.
Yeah, so if we're getting exactly up to like 99.9999999 and not hitting the boiling point. So we would have to do that with a thermal bath system where we're not locally heating one side of an actually boiling part of the water, right? Because whenever we heat water, we heat it from one side to the other. So one side gets hot first. That side will boil first. All of our theoretical calculations are doing like uniform thermal delivery, not practical in reality. So it has, like these ice melting problems, like all of the ice melting at once has intuitive trouble because we never experience it that way. We always melt the edges of the ice first.
I do have one question about
Sure.
this problem. What if there was still ice left? How would you find it?
So if we have ice left, does that happen in number 11 by any chance?
11 is not an ice problem.
Okay. If we have ice left over, our setup here, this first line in of our Q in, Q out, ends up being different. Because if there's ice left over, this warming thing doesn't happen, and that N is not all 46 grams. So the places where things change, if we had an ice left over, the two things that change is this term doesn't happen at all. That term just doesn't, because we're not going to have any leftover energy to heat like the water. And then this number,
Is your missing number?
yeah, is less than 46 grams, but we don't know how much less than. So that's how things change if we had that ice left over situation. Our unknown variable becomes how much ice does melt. And so what we don't know changes, right? And that's where, when we did our thinking, I was like, oh, mass of ice is equal to 0. In this situation, T final is equal to 0. This thing becomes the question. Okay. Wow, I just looked at that on the recording. It looks like a mess if you weren't here during that problem. Other questions about this problem? Again, this is a pretty tricky problem. Let's try number 11. And did you have any questions you wanted to add to the list, or did you have something else? Okay. No, we can do that. Can I do number 11 and we'll take care of that? Is this helpful for you too? Cool, okay. So let's take a look at number 11. I'm going to erase all of
I'm
this.
just going to show it.
Okay, give me just a second to erase first.
It's a pressure question.
A pressure question. I wonder if it's just a concept trick question. Let's see here.
It could just be I'm not understanding pressure.
So, oh, this is a vapor pressure question.
Yeah.
So, a 23.8 degree vapor pressure at 23.8 degrees Celsius, the vapor pressure of isopropyl alcohol is 40 torr. At 39.5 degrees Celsius, the vapor pressure is 100 torr. What's the enthalpy of vaporization of isopropyl alcohol? Where do we even begin? Is there any, so like when I have a problem like this where I'm like, I don't even know how to begin this. Do you know how to begin this problem? Okay, some of you do, some of you don't. Here's how I like to think about it, and this is a trick I like to use that works for, sorry, I'm making sure it's still recording. I've had some problems in the past. Okay, this works for, so we did number 9, we're doing number 11. 1.2, number 11. This works for pretty much any class. History classes, English classes, philosophy classes, chemistry classes, physics classes. At least in my mind it does. I think about what information I'm given explicitly, the result I'm trying to get to, and then there's going to be some stuff missing in the middle that the problem's actually trying to get us to think about. So what information, just what numbers are we given? What's explicitly given? It's isopropyl. I know we've got one temperature.
You have vapor pressure of isopropyl alcohol. You have the atmosphere.
What number do we have for the vapor pressure?
You have 23.8 degrees Celsius for the vapor pressure of isopropyl alcohol.
Well, at that temperature, we're given a pressure in torr.
40.
40 torr. And then what else are we given?
You have another temperature and pressure.
Okay, so I'm going to go ahead and label these T1, P1, T2, P2. What's our second temperature?
39.5 and 100 torr.
And then you have to ask, like, are there any like terms? Well, here you have
Okay.
negative half T1,
Degrees Celsius.
positive 1.
Okay, so those are the numbers I have. What result is asking? It's asking me to get the delta H of vaporization. Somehow, these numbers can be put together to get delta H of vaporization. There's something in the problem it's not telling us. That the question is being like, hey, can you, from this context, can you tell what's going on? And so that's where, do I have the right equation? I do have the right equation sheet. So I pull up my equation sheet, and I just start looking for something that's got all of these variables in it. Right? And the more familiar you are with the equation sheet, the easier this is to do. I start looking through that. I've got an HP, EPV, EQW, WPV, MC delta T, and delta H. Oh, there it is. Natural log of P2 over P1 equals negative delta H vaporization divided by R times 1 over T2 minus 1 over T1. So this is the Clausius-Clapeyron equation. So inside of here, there's nothing in this problem that says, use Clausius-Clapeyron equation to blah, right? It's assuming that we can tell from the context that there's this implied natural log P2 over P1 is equal to negative delta H over R, 1 over T2 minus 1 over T1. Nothing in the problem tells us this equation. We did talk about it briefly in class as we were talking about phase diagrams. But most of the way we use, like, again, phase diagrams is where this is conceptually interesting. For me, these problems are kind of mathematically boring. Because after you get these variables and recognize it, it's like unit conversion plug and chug. So I didn't spend time doing that in class, because once we have this, notice it's already in torr. I'm going to have a ratio of pressures. Units will cancel. It doesn't, as long as these are in the same units, it doesn't even matter what units. It's atmospheres, torrs, millimeters, mercury, kilopascals, bars, right? Whatever. As long as the pressures are the same, that unit's going to cancel, so I can take the natural log.
What is R?
R is the ideal gas constant. So, and I have to make sure there's actually two different R's, whether we're talking about energy or we're talking about pressure. Sorry, energy or liters and liters, volume, and so the units are, there's two different R's, right? And so this is another thing that we have to pay attention to. This is also implied. I've got one R that's going to be the 0.0821 liters, atmospheres, Kelvin, mole. I've also got an R that is equal to 8.314 joules, Kelvin, mole. Now, we already said pressure cancels out, so do I want to use an R that has a specific pressure in it? No. So we're not going to use this R. That R is not going to be useful. When I look at this, joules per Kelvin is going to cancel out. 1 over Kelvin, I've got my 1 over T, my 1 over T, so that unit will cancel out, and I'll just be left with joules per mole.
Which is what you're looking for.
Which is what I'm looking for. So that R makes more sense. But notice, this is not a delta T. This is a 1 over T minus a 1 over T. Not a delta T. So I have to convert both of these temperatures into Kelvin. Otherwise, I'm going to have a problem. Right? Also, not explicitly given in the problem, just implied. It assumes in the problem. It's like, hey, you've been coming to class, you've been reading the textbook. You know you need Kelvin. Right? There's nothing in the problem that tells us we need to turn Celsius to Kelvin. It's just implied. It's this implied information that it's checking for. And pretty much every problem, and this is the reason I like thinking about this. I think about a lot of problems this way because This is kind of every problem you run into in college classes do this, where the teacher knows what information is being implied. After you graduate and you go get a job, this is actually almost every problem you're running into, except no one knows what's implied. Right? That's the ability to kind of see the missing pieces, the stuff that everyone else didn't think of. That's what makes a college education like valuable. Is being able to look at a problem and be like, hey, did you think about this? And they're like, oh no. Right? I just forgot. Or like, I didn't even think of that. Right? This missing stuff in the middle. I know where we are. I know where we want to get to. What's not being told to me? What's missing? What's not said? Should we go through the math for this? Let's do it real quick. So we're going to have natural log of, I'm going to put, I think it works out better if we have the higher pressure on top. Yeah, that'll be better. Either way works as long as we're consistent, but then I like to not have negatives. I like to not have fractions. So I'm going to have natural log of 100 over 40. My units will cancel. I'll have negative delta H over 8.314 joules mole. Ooh.
Keep them consistent like P1 and T2, like P2 and T2.
Joules, Kelvin, mole.
Like in derivation, like if you flip them to the P1.
We're not doing the derivation. Did you do the derivation already?
351, we had to do it.
Yeah. Okay, that's what I thought.
Ordered, the negatives cancel.
Okay. So let's see here. T2 is going to be my 395 as long as I'm consistent. 39.5 plus 273. Oh, yeah, 312. And then I'm going to have my 23.8 plus 273. So 1 over 296.8. Again, technically it is 273.15, rounding errors for what we're doing. So I'm going to go ahead and do 312.5 inverse minus 296.8 inverse. This is going to give me, oh yeah, that makes sense. Okay. This is vaporization. This parenthesis, assuming I did the calculation correctly, is going to give me, I'm going to go ahead and put it into scientific, negative 1.692 times 10 to the minus 4. Over here, 100 divided by 40, natural log, gives me 0.9163. I'm going to go ahead equal to delta H over 8.314 times, I'm going to move.
Don't forget the negative.
Thank you. Right, those negatives are going to cancel out. Times negative 1.692 times 10 to the minus 4. Negative will cancel out. So I'm going to multiply, divide, that'll get me delta H. So multiply by 8.314 divided by, I'm just going to divide by 1.692 times 10 to the minus 4. And I'm going to get 45.02 kilojoules per mole equals delta H, where my negatives canceled out of vaporization. How can we tell if this is a good answer or not? Do any of you have a good sense of what a delta H of vaporization should be? No, me either. But here's what I do know. The delta H of vaporization of water is 40 kilojoules per mole. Come on in. The delta H of vaporization for water is 40 kilojoules per mole. This is isopropyl alcohol, so it's going to have like London dispersion forces, dipole-dipole interactions, hydrogen bonding forces, and it's going to be heavier than water.
So it should be higher than water.
Kind of makes sense that it's a little bit higher than water. This is a problem, not all the classes do this type of problem. You're in 128? Perfect, okay. This is a problem that my class still does. It's kind of a plug and chug once you know how to do it. Questions about that? Okay. Again, the big problem with this is, back to where we were at the beginning, we had no idea how to do it, it's that process of, for me, this, and everyone has different ways where when you're stuck on a problem, how do you deal with it? Mine is, what do I know? What am I trying to get to? And then I look for an equation on the equation sheet that has all of those variables. And that's usually a good place to start. So that was number 11. We're working through the homework problems in my class, but do you have any specific questions you want to add to the list?
I will open my computer.
Okay. I'm going to erase, well actually I'm going to pause, we're going to look at your LabPal thing. Okay, so back to it, we're doing number 15 from 1.2.
All right. So this is the Mountain Climbers Brewing Tea by Melting Snow question.
Okay.
So there's a stove that burns butane, C4H10, which has a heat of combustion of negative 2,878 kilojoules per mole. And then the initial temperature of the snow is negative 20 degrees Celsius.
Negative what?
20, sorry.
Whew. I was just like, that cold, huh? Okay.
And we need 80 degrees Celsius to brew tea. How much heat in kilojoules is needed to turn a cup of snow, or snow into a cup, 273 milliliters of water hot enough to make a cup of tea?
Okay. So this will be kind of like the question you were asking from MQ2, where we want to figure out how much butane we need to burn to heat up the snow, melt the snow, and then heat up the melt.
Oh yeah, I just did that question.
Oh really? Okay, cool. Did you get it right? Okay, cool. Well, we're about to do it.
It's still a good question.
Okay. So again, there's a lot of different ways we can frame our thinking here. I still think of it as Q ins and Q outs. And I'm going to think about, I'm going to think mostly about the snow system. So I need to do heat, melt, heat. So I'm going to end up with 3 different Qs here. Q1, Q2, Q3. At the same time, the butane is going to be my exothermic system. And it's just going to, oh, actually, it's not going to be like that. It's not going to be changing temperature. It's just going to be a flat Q4. So this is going to be my Q out. It's just doing a chemical reaction. It's not cooling off. And this is going to be my Q in. And then I just have to keep track of everything. So Q1 is going to be MC delta T. I erased the 2 there. So we're going to have 273. Now this is ice. It's frozen. So this is going to have a different heat capacity. Fortunately, I have my equation sheet handy. For the heat capacity for solid water is 2.1 joules, grams, degrees Celsius. Put my units in here, that's grams. Because again, implied information, right? I'm assuming that you all remember the density of water is 1 gram per milliliter. So we've got our 273 times 2.1 times our delta T. That T final is going to be 0 minus our T initial, which is going to be an awkward double negative, minus negative 20. Right? So we're going to put energy into that happening. Q2 is going to be enthalpy of melting, reverse of fusion. That's going to be, again, the 273 divided by 18 to get it into moles, times the heat capacity for fusion, which is... Yeah, I was just trying to remember if I did it. No, that was ice melting, so we're still okay. It's melting. I was like, did I use the wrong number in the last problem? Different problem. I'm going to, again, one of the big problems people have is the mix-up of kilojoules and joules. So I'm going to go ahead and right away turn this into 6010. So it's in joules per mole. This is going to be grams. This is going to be grams per mole. Grams will cancel, moles will cancel, then look at the energy. Q3 in this case is going to be heating this up. So it's going to be 273. It's already turned into liquid. So it's going to be 4.184. And it's going to be final temperature. We want to get all the way up to a steamy 80 degrees Celsius, up from our 0 degrees Celsius. So these should all end up as positive values because these are all places where we want to put energy in. So I can do a quick check. negative, negative. That first one's going to be positive. This is, I have to be careful with my delta H of fusion, understand whether it's the melting process or the freezing process, because it's positive delta H of fusion, negative delta H of fusion. This is the melting process, so we want to put energy in, it's positive. And then 80 minus 0, that one also ends up positive. All of these should be equal and opposite to Q4, which is just going to be an N delta H. Where the big question here is, how much butane do we need? So that's going to be the question mark. So I'm going to plug in, so I've just got to find N, making sure I don't mess up my units. So that's going to be 2878000 if I'm doing everything in, if I'm doing everything in joules, which I switched this to joules. Now that I'm looking at this with that 2878, it probably would have been easier to switch everything to kilojoules, because I'm going to have a bunch of extra zeros. But it'll be fine either way, as long as I pay attention to my units. So, tracking?
Yeah.
Where'd it go wrong for you?
I think it was just because it was closely pressure questions. I wasn't sure if it had anything to do with
Oh,
it.
no. Right, now, again, because technically the water melting does change volume, and so there could be some like work thing in there, but not really. The place where the pressure would have become an interesting kind of tie-in is when we hit the boiling point, because that's where that pressure, the Clausius-Clapeyron equation, is really how do we change the vapor pressure of water and why does that matter? Yeah, no, this one doesn't use that. I probably just put them in order that we covered things. And,
Okay, yeah.
yeah. So let's go ahead. Let's still finish it off. If I can find a calculator. Let's get these numbers. 273 times 2.1 times 20. I'll just put the numbers over here so it's less cluttered. That's going to be a 1.146 times 10 to the 4. 273, divided by 18. Sorry, I just saw 273 and it freaked me out because that's also the Celsius to Kelvin conversion. My brain was like, I'm not switching temperatures. Divided by 18 times 6010 is going to get us 9.115 times 10 to the 4. Yeah, I should have done this in kilojoules. It would have been way easier. And
You
then
can still convert.
273, I'm going to, times 4.184 times 80. Whoa, I missed something. I had times 10 to the positive 8. I think I did 4184 with one decimal. 273 times 4.184 times 80. There we go. 9.138 times 10 to the 4. Right, so 11 kilojoules, 91 kilojoules, 91 kilojoules. Would have been easier. Over here, yeah, I'm converting all of them. Let's do it. I'm going to erase this kind of like energy flow picture, this kind of energy diagrams.
That's useful for you to know how many stages you're going.
Yeah, it just helps me keep track of how many Qs I should have and what equation I'm using for the Qs. So let's go ahead and do 11.46 kilojoules plus 91.15 kilojoules, so much easier, plus 91.38 kilojoules is equal to negative N times negative 2.878 kilojoules per mole. And again, this is part of why I really like to have my negative sign on the Q outside. My negatives are just going to cancel out. And then I'm not going to have to worry about plugging it into my calculator or carrying it around. You don't have to do it that way. The negatives will cancel because multiplying, dividing works. It just makes more sense for me. So we'll do 11.46 plus 91.15 plus 91.38. We want to get 193 kilojoules of energy divided by 2878.
This is like the first class where my class notes are.
0.0674 moles. Right. So that's the number of moles. Does this ask for number of moles or number of grams? Grams?
Yeah.
Awesome. So now we have to take that moles multiplied by the molecular weight, which is going to be 4 times 12 is 48 plus 10 is 58. So times 58. We need 4 grams of butane, 3.9 grams of butane. Now, if you're doing mountaineering and you don't have someone to carry all your stuff for you, you actually want to keep track of like how many grams of fuel you have, how many grams of fuel you're using for something. And then you want to pack like 20-30% extra. But you might actually care about that if you're doing like serious, like if you're worried, like there are people who worry about like every gram they're carrying. I don't do backpacking that
I did a
serious.
week-long one and we didn't worry that much about it.
In alpine conditions,
We were going over hills and stuff, so
okay.
I don't.
But not like
remember.
glacial.
No.
Okay, yeah. This is like if you're going up, like this is where I said if you don't have someone to carry your stuff. This is like if you're going up Everest and you're carrying all your own stuff. You're not hiring people to carry your stuff.
Super lightweight.
Yeah.
Every ounce matters.
Yeah. Questions about this one? Or are we ready to check out number 16? Question.
But for that one, for the negative n, was that coming from the negative q surrounding?
Yeah, so I call it Q in, Q out in my class, just because I
Okay.
think about it in terms of energy flow. So I do Q in equals negative Q out,
Okay.
and you could also think of it as Q system equals negative Q surroundings.
Yeah. Okay, that makes sense.
If energy is flowing out of the surroundings into the system.
Yeah,
I find system and surroundings to be a little bit more abstract. In this situation where the reaction is like, in this situation, I guess if I was thinking about it, I would call the butane torch my system and the water I'm heating the surrounding. And so I might want to switch these labels, but it doesn't really matter. I just switch it to be the same thing again. So this would be my surrounding water, and this would be my system. My system is losing energy to the surroundings. Same idea though.
I have to get to my next class.
Hey, no worries. I'll post this for number 16 for
Okay,
you.
perfect, thank you.
Okay. Question?
I do have another
Yeah.
related, like last one. Okay, so in the wrong case, the solids will have higher like IMFs than liquids.
Debatable, but okay. They have a lot more energetic interactions, right? So, for example, if you're thinking about liquid H2O, I guess water is a bad example because water kind of breaks the norm. I think generally you're correct. I was thinking about water.
Okay. Or I thought that was like the norm. So my question was, like, the enthalpy of, is it like fusion to go from solid to liquid?
Yes. Yes. Fusion.
Is that, it's so high because it has to like break whatever interactions there are, right?
Yeah, no, we're not fully breaking them because again, if you're thinking about water, your H2O molecules are kind of locked in position with those hydrogen bonding forces, and when you go to liquid water, there's still hydrogen bonding forces there. They're just not as organized, and so there's that kind of like there's that crystal structure energy that we have to think about as well.
But then, are there certain materials where there is basically no difference, and so like the melting point is just, it would then become.
So this is something we're going to spend more time talking about in 125 and 128 pretty soon, where we're really getting to this idea of lattice energy, where instead of thinking about just like one bond, we have to think about like the bulk material and kind of the benefits of molecules being next to each other in an organized way, versus a disorganized way, right? So when you're a liquid and you can kind of tumble around, you've got some different energy considerations than when you're a solid locked into a rigid structure. Now, it sounds like you're talking about what we call ideal situations, where the IMFs are approximately the same between the two situations. We usually look at that when we're looking at the liquid to gas phase change, or when we're looking at liquids mixing. I have to review my notes. But there's places where we're looking for ideal solutions where that delta H change is small. So like the IMFs are approximately the same between the two. I just thought of where I was thinking of it. I'm reviewing notes for my lecture tomorrow, on Thursday. What's your question?
I guess I was introduced as fusion is when you kind of like the way to think of it is you could break the interactions to solid and then form the one that's a liquid.
Mm-hmm.
But is it? It can also just be like the thermal energy happens to be enough to where those same IMFs just are now as a liquid. Like,
Yeah. Well, so and this is right. So you're getting to the idea of Hess's law, some of the things we're about to do, where we could think about it in terms of break down the solid into all of its things where we've gotten rid of all of the IMFs, and then we bring the IMFs back. So we have this positive and then this negative, and the difference between the two would be the delta H of fusion, whatever's left over. And that's a fine way to think about it. So in that case, it's not just when you're doing the breaking part for the solid, it's not just the IMFs, it's that bulk crystalline property.
okay.
And so there's a little bit extra there that's really difficult to get at, and that's part of what we do when we start talking about ionic compounds. That delta H of lattice is really difficult to get, so we do a multiple step process to try and understand it. Because it's not as simple. Like, so for example, when we're looking at like sodium chloride, it's like Na plus Cl minus a billion times. But there's some extra benefit of having other NaCls around that first NaCl that we're not taking into account in our kind of like simplest picture in our mind.
Okay.
And so that extra energy is the lattice energy. Did you already get to that part?
Yes, I'm also listening to what you're saying.
Cool.
Interesting to hear it. I think the hardest part about this class, honestly, is keeping track of all the signs, positive and
There's a
negative.
lot, like positives and negatives is a big issue with this class.
Yeah.
Okay, if we do number 6, did that make sense?
I think they need a better question.
Okay, definitely come back. I'm willing to talk about it more. I also want to get through number 16 and number 21 before, I don't know what time it is. Oh, we got plenty of time. Before people have to go, though. And then did you have a specific question or?
Yeah, I had a question from the quiz that we did.
Oh yeah, we can do quiz 1.
Yeah, quiz 1.
Which one?
There was question. Sorry, let me check.
Is it number 2?
Number 3. Well, yeah, number 2 and number 3.
Lots of people got number 2 wrong. If I've got them in the right, is that the multiple choice one?
Yeah.
Yeah, lots of people got that one wrong. Okay, so we'll look at those as well. Let's do number 16, then we'll do the other classes, number 21, which might be our number 16. We'll see. It'd be nice if they overlap. And then we'll look at those quiz problems. I'm going to erase.
Oh, right.
Oh, that one. Okay. The person who was asking about number 16 took off. Does anyone have number 16 from 1.2 available?
I put my computer away. It's on.
Can you open 1.2? Thank you so much.
It was. I think you just answered it because it's.
That was number
It's
15,
number
I
16,
thought.
right? The
Yeah,
1.2?
number 16.
Yeah. It says find the in grams.
Oh, I did both. I did
Yeah.
15 and 16 already. Well, that's even better. Okay, so let's go ahead and look at your question from Master Question 2.
Alright.
Now this is from another class, but it's another like 125, 128 class, so it's still relevant. I think it's number 3 from the quiz. We'll see.
Quickly was question 21. A one beaker contains 21 milliliters of 1.6 molar HCl. A second beaker contains 54 milliliters of 0.04 mole of NaOH. Both solutions, or initial temperature was 20 degrees Celsius. We pour both beakers into a large insulated container, which contains 9 grams of ice at negative 60 degrees Celsius. Calculate the final temperature. Note that enthalpy.
Wait, what temperature was the ice?
Negative 60 degrees.
Negative 60 degrees Celsius. Okay.
Note the enthalpy of neutralization is negative 57.3 kilojoules per mole. Should I give you an idea of how I tried to figure it out?
Yeah, tell me what you're thinking.
My first thing that I did was I wrote the reaction out.
Uh-huh.
So I could figure out what the coefficients were.
HCl plus NaOH goes to H2O plus NaCl. Whoa, that L went weird and that A went weird.
And then from there, since we have milliliters converted to
Was
grams.
this 0.04 or 0.4?
Oh, point 0.4.
0.4, okay, because I was like, that seems like a small amount.
0.4, yes.
Okay.
What I did is I wanted to find the limiting reactant.
Uh-huh.
So first thing
Is this like number 3? Okay, no. Okay.
So, 21 milliliters is 21 grams, 54 milliliters, 54 grams. And,
Keep going.
okay, so what I did from that, and you need to use the molar conversions you have, and you know that molarity is moles over liters.
Okay.
So, you use the 1.6 moles of HCl equals,
Ooh, hold on. 1.6 moles.
sorry, molar.
Yeah.
1.6 molar.
Okay.
HCl equals unknown moles over 0.0021 liters.
Perfect, okay.
And then
Solve for the number
multiply.
of moles, yeah.
Yeah,
Okay.
you get the moles.
So let's get the number of moles. 0.021 times 1.6 gets us. So our HCl, we've got 0.0336 moles. Our NaOH, we've got 54 times 0.4.
Yeah.
We got 0.0216 moles.
Yes.
Limiting reactant is?
Because it's a 1-to-1 ratio, you know it's the NaOH.
Great.
Okay. So yeah, what I did from there was I found out the limiting reactant. Since you know the limiting reactant, you know the enthalpy of neutralization.
Mm-hmm.
You could figure out the Q system
Okay.
from that. Because Q
I'm going to call it Q reaction.
or Q reaction.
Right?
Yeah.
Just to be a little bit more, because like, I'm not entirely sure where I want to decide the system and the surroundings yet.
Yeah, you're right. Q. I should write them for myself. Q,
Right, and I use a lot more subscripts than other people use, but.
It's. I'm gonna write that down. So Q reaction, we know that that's equal to moles times the enthalpy change, and so you just can rearrange that.
Yeah.
So then you know that enthalpy change of the reaction is negative 57.3. So then how you could reset that is equal to Q. I just rearranged the problem.
Yeah. So, N delta H?
Wait,
Sorry.
N delta H. Yes.
Okay.
So we're trying to figure out what Q is. So you just multiply N
Yeah.
times delta H.
And I had
Exactly.
a typo in mine, so
Sorry,
this is going to be
I didn't mean to
1.2.
take one step forward. I looked at it wrong.
1.23, negative 1.23 kilojoules of energy.
Yes, that's what
Okay.
I thought.
So here, let's stop here for just a moment, right? So if we were just doing this as pour the two things together, then this would be an exothermic reaction the energy would go into the water surrounding the HCl and NaOH, right? Because these are aqueous solutions, it's mostly water there. And we see the temperature go up.
Yes.
Then,
Yes.
right, because it's exothermic.
Yes.
And so it's like this little bubble of reaction giving energy off into the surroundings.
Okay.
If you do a calculation, so if you figure out how many grams, if you take that number of moles of NaOH, that 0.0216, and you multiply by the molecular weight and then divide by the density to get the volume of it, it's like 0.2 milliliters. Right, so out of that 54 milliliters, like 0.2 of it is the actual like NaOH.
Okay.
The rest of it's just water.
Okay.
And that heat would go into the water. And we'd see the water get a little bit hotter than 20 degrees Celsius. However, we're then throwing 9 grams of ice on top of it. So how many Qs do we need to keep track of for this?
4.
Let's see. 3 more in addition to the Q reaction, I
Okay,
think.
yeah, 4.
Right? Let's keep track of them all. So we're gonna have the Q. Well, I gotta draw pictures for this.
So this is the first Q we have.
Right?
Q reaction.
That ice is gonna, like, if there's ice left over, that ice needs to heat up. I think we're just gonna heat the ice up. I don't think we're gonna melt it all, but we'll see. No, we're just gonna melt. The ice is gonna heat up, the ice is going to melt, and the ice could warm up some. Versus reaction, and then losing energy. Right? Because once this reaction happens, we've got this body of water that's at, like, let's say 22 degrees Celsius. That water is then going to lose energy to the ice.
Yes.
So we've got our system, we've got our surrounding. Our system is going to be made from 2 Qs, the reaction and the hot water from the reaction. I don't know. I don't like system and surrounding. I'm like,
It's fine.
because like I'm like, is the system the reaction or the ice, or like in this situation where there's so many different bits, like I lose track of which is system, which
That's
is
what I want
surrounding.
to get better at, is writing my things. So that's why I've been starting to write as like you're saying Q reaction. And
Yeah.
I write as like Q heating heated water. Q
Yeah.
melted ice.
Perfect.
Like that's what I've been trying to do more.
Okay, so I'm going to do the same thing we did for the first problem we did during office hours. You weren't here for it, but it was does all the ice melt?
Is like the MCAT, is like
Yeah.
all the different steps.
Yeah.
Okay.
So in this situation, I'm going to say we know how much energy comes from the reaction. I want to figure out how much energy it takes to melt all of the ice. And then I'm going to see what we have. So to melt all the ice, we're going to have, I'm going to call it Q1, Q2. Right? I just need those 2 Qs to melt all of the ice. So it's going to be 9 times 2.1 times T final 0 minus negative 60.
Yeah, that was my Q heating ice. That was
Perfect.
My first one.
And then my Q2 would be 9 divided by 18 times 6.0. Let's be consistent. I'll
This is
call
what I
it.
did.
I'm
This first.
going to do this
So
one.
that's the enthalpy of diffusion times the
equation
mole.
first.
Yeah,
So this is
6.01.
Like the no, and then this
Per mole.
which is like this is.
Yeah.
And I just want to figure out what those 2 things are first. To tell, is all the ice going to melt? I think it is. Because we got 20 grams of water, but we'll see.
I ended up. Well, you have to wait and see. I
I'm just guessing. Divided by 1,000. So this is wild. Because there's only 9 grams of ice, this only takes, did I divide it by 1,000 or 100? 9 times 2.1 times 60, because the negative cancels out. Yeah, so we get 1.134 kilojoules just to warm the ice up. 9 divided by 18 gets us 0.5 times 6.01 gets us 3.01 kilojoules of energy just to melt the ice.
Yes.
So you still have ice.
Well,
So.
maybe.
That's interesting because the energy needed to melt the ice is more than
Yeah.
than the amount of energy that's released into the water.
Well, hold on.
Or is that what that is representing?
Right. Then this negative 1.23?
Yes, that's
Yes.
that's the ice's energy being.
Highest rate itself by magnitude. Yeah.
That's wait.
Now, there's something else we have to keep in track when we're doing this comparison, right? Because it's not just the reaction that we have energy to lose, it's also the water cooling off.
Yeah.
So we have to do, which is where I'm like, oh yeah, all the ice is definitely going to melt.
Okay.
Right, so we're going to have our Q reaction equal to negative 1.23 kilojoules. But then we're also going to have our Q of our water cooling. I'm going to call it...
I call it melting ice.
This is not melting ice. This is the Q of the solution
Oh, the Q.
cooling,
Oh,
right?
okay.
This downward arrow here.
Oh, I see.
And that is going to be 21 plus 54 is 75 times 4.184 times how much energy could we possibly lose. I'm going to do T final 0 minus T initial of 20. And I'm going to figure out the maximum amount of energy we could lose. And I think the energy we can lose is going to be bigger. So this is just figuring out, do I need to worry about this last bit or not?
What is this? That's
75 is the 21 plus the 54,
okay.
right? For the total mass of the solution that can cool off. 75 times 4.184 times 20 negative, divided by 1,000. The water could lose 6.28 kilojoules of energy. Now, heating the water up and melting the ice, melting the ice and then, or heating the ice and then melting the ice takes less energy. So we know, right, so if I draw this to scale, not to scale, but if I draw this a little bit differently, let me just give myself a little guiding line real quick, right? Reaction, cooling, is not going to get all the way to 0 there. Really, it's going to go reaction, cooling to some point, reaching a different T final, not reaching 0 degrees Celsius.
Oh, yeah.
Right? What's that?
That's how I got that wrong.
Right? It's not going to hit 0 degrees Celsius. So that means I'm going to need an extra Q here,
Okay.
and my T final is not going to be 0.
Okay.
So it's not going to lose all 6. So this is kind of exactly what we saw at the beginning, the first problem we did during office
This
hours.
is an intermediate step.
This was an intermediate step. So this thing is not actually correct. This 0 is not really going to go to 0. This number is not going to be that low.
Okay, so you just get rid of that one.
So I'm going to get rid of that. And instead of having a 0 there, that was just me checking if I had enough energy. So in this situation, did you have a question as well?
Yeah, so so the T final, like, is it gonna be, like, based on the diagram, is it gonna be less than 0 or more?
Greater than 0. This is temperature up on this side, right?
And this is of the solution at the end, or like?
Of the total solution at the end. So this is going to be my T final that I need to find. It's going to be
Oh,
this.
so we still don't know if there's ice left over or not. We're still figuring it
Well,
out, or-
from the calculation we just did, no ice left over.
Okay.
It's all going to melt and it's going to warm up some. Now the question is, how much is it going to warm up? These numbers are all still true, but I need another Q in here. I'm going to do it in orange to kind of represent that last step. I'm going to need what I call Q3. That's going to be 9 times 4.184 times T final minus 0.
Okay.
Right, so that ice, this is my ice system. I had to warm it up, I had to melt it. After it melts, it's going to warm up some, and this is the warming up some. How much? I don't know, that's what I got to figure out. That's what the T final is. At the same time, reaction kicking out energy, and then technically there's like another picture I could do here where the reaction is like heating things up, but it's reaction kicking out energy and then cooling off. and I have to figure out where that T final is, where those two things balance out. And you'll notice all numbers, all numbers, all numbers. The only thing I don't know is T final.
Yeah.
So now I can set this equal and opposite to that. Notice both of these numbers are going to end up being negative because T final has to be less than 20. So I'm going to have negative numbers equal and opposite to positive numbers.
Okay.
And so I would call this my system and this the surroundings in that case, which is weird. But
Yeah, it's a little. I'm just trying to keep track. So, what you're saying is you have multiple Q's, you have multiple Q's during your reaction that represents all the different stages of the reaction when it goes from when it's solid to a solid, solid to a liquid, a phase change, and then it's a liquid to a liquid again at a higher temperature.
yeah, so it's solid going through a temperature change, solid to a liquid phase change, liquid to a liquid at a higher temperature.
Yeah, so it's
For the ice, so it's 3 Q's just for that ice.
Yes.
There's 2 on the other side.
What's that?
And then there's 2 on the other side.
And then there's 2 on the other side. There is the reaction and then the water from surrounding the HCl and the NaOH, all that water surrounding it, cooling off.
That's the part that's confusing, is keeping track of all of them.
Yeah, and that's part of why I like these kinds of pictures, and I try to avoid system and surrounding,
Yeah.
right? Because there's so many different bits that we can call our system or surrounding. I like to think about it as what's losing energy, what's gaining energy. So these both are losing energy. This thing is gaining energy.
Water's losing energy.
The water's
Ice
going to
is
be
gaining
losing
energy.
energy. The ice is going to be gaining
And it's
energy.
gaining
Exactly.
It's gaining the energy so that it could break the intermolecular bonds and phase change.
Mm-hmm.
Okay.
And then warm up some.
So when you do like the Q in, Q out, which one are you gonna make negative?
I like to do the thing that's losing energy as the negative, right? Since this is already negative, I know this is going to be negative. I'll get rid of all of those negatives by making this side
So-
negative.
When it's losing energy, that's endothermic, right? Or no, that's when it's absorbing energy.
Correct. So
Exothermic
endothermic
is
is,
when
yeah.
okay, yeah.
So how would you set this up if you're?
Okay, so I'm going to erase my picture in the middle if that's okay.
Yeah, that's fine.
So I'm going to erase this stuff in blue. We did the stoichiometry already. I'm going to switch back to doing the problem in blue because I feel like
This
choosing
is a
colors
hard
again.
question.
Right, so it is and it isn't, right?
It's just a lot of
It is. There's a lot to keep track of. There's a lot to think about. But ultimately, like, the calculations themselves aren't that hard.
Yeah.
So we're going to have 1.134 kilojoules plus, I don't know why I'm doing it this way, 3.01 kilojoules. I don't like that. I don't know why I did that.
Okay.
1.134 kilojoules plus 3.01 kilojoules plus 9 times 4.184. I'm going to do that math real quick. 9 times 4.184 is going to give us 37.7 T final. I'm going to skip the minus 0. That seems silly to include. Is equal to negative 1.23 kilojoules. Oh, hold on. Didn't give myself enough space for the negative sign.
No.
Don't forget your negative quantity. Negative 1.23 kilojoules plus 75 times 4.184. 313.8 T final minus 20.
And now it's from.
Exactly. Right, so reaction is going to kick out energy. The warm water, the reaction water, is going to kick out energy. They're both going to kick out energy into the ice to heat the ice, melt the ice, warm that melt. Lots to keep track of.
Yeah, it's like you said, it's like not hard to solve.
Okay,
It's just
yeah.
steps.
So let's see here. 1.134 plus 3.01. Whoa, that's not right. 1.134 plus 0.01 4.144 kilojoules is equal to, yeah, let's do it that way. It's equal to, no, let's not.
Plus 37.7.
Plus 37.7. I was going to do too many math steps at once.
Just add all those together.
1.23 kilojoules minus 313.8 TF plus 313.8 times 20. Negative and negative will cancel, plus, did I do that right?
I think you should do 1.23 minus 3.18 and then put that quantity times TF, because the way you're written it is technically not what you're doing.
I just followed this out. 3138 TF plus.
You made the positives negative, then FOILed it out.
Oh.
Yeah, so I foiled out the negatives. So this became positive, that became negative, that becomes positive.
Okay.
It's just a bit confusing.
Here,
to
I'll do it
that
this
way.
way. Better?
Yeah.
Okay, sorry. Again, this is where I do too many math steps at once. Often, sometimes it works out great for me, sometimes it leads to really bad mistakes. And I wanted to recheck this calculation. I guess 300 times 20 should be like 6,000. I guess that's fine. That just seemed like a really big number. And now I'm just solving, that's why it's a really big number. Right, this is in kilojoules, this is in kilojoules, this is in TF.
Joules per.
This is in joules. I need to divide this by 1,000.
Oh, I see.
And I need to divide this by 1,000. And I need to divide this by 1,000.
Oh, yeah. That's a good point.
Right? All of those MC delta T's need to be converted to kilojoules. Otherwise, it'll be a total mess.
Or you'll have to convert kilojoules to joules.
Yeah, either way. But again, we want to make sure we're keeping track of those units. I still have another class tonight. Jeez.
What are you teaching?
It's the I do the LA's pedagogy class. So it's like, how do you teach? How do you learn for the LA's? Okay. Hey, y'all should sign up. It's a great class. I mean, you should sign up to be LA's. Yeah, it's a great idea. You'll learn this stuff way better if you become LA's. Okay. So now we're doing some algebra. We're going to do 4.144 minus 1.23.
He teaches how to be a TA.
Minus 6.276.
I didn't know you need training for that.
Well, because you have to know how to teach other people, right?
Well, I'm a TA. For that
Oh,
part.
it's different in the A chemistry department.
Oh, okay.
Yeah.
I feel like I'm about to make a mistake someplace.
Sorry, I just got really confused really quickly.
No, that's
On that
okay.
TA.
That's positive.
It might be easier to just make the kilojoules into joules and then at the end divide everything by. That's what I usually do.
Yeah. Let's do that.
Because I
got
tried to
so
do it the
excited.
other way once, and then like my answer was wrong.
Yeah, because the kilojoules to joules, you just move the decimal point, and it's basically already there.
Yep. So let's just do this. This is going to be 1, 2, 3. So that one's going to be good. This one's going
You
to be
need an extra 0.
1, 2, 3, 0. Now everything's in joules. Okay, but I was still
Except for the notation that says kilojoules.
feeling. Yeah, thank you. I was still feeling like I felt like I was going to end up with a negative temperature. Oh, it's because I didn't carry through my negative sign properly. That's why.
No, because you took it out, so you'll still end up with a negative one. Cause
Yeah. So this is going to be equal to 1230 minus 313.8 plus 6276 equal to. Oh, jeez. Am I getting tired?
I have a class after this, so.
T
Oh,
final plus 6276 equal to 4144 plus 37.3 T final. Okay, now I'm at a spot where I think I can do the rest of the math. Because I'm going to just put those three numbers together, add that over. So I'm going to do 6276 plus 1230 minus 4144 divided by 390.
In parentheses, make
Yeah, let's do that.
37.3 plus 390.
Yeah, I got it in.
351. I almost had it. 9.5 degrees.
Oh, I did something wrong. What was?
I don't know. Did I do something wrong, or did you get it right, or
Oh,
do
I
you know if you
didn't-
got it right?
I did something wrong. I
Okay.
put it in kilojoules.
So I got 9.5 degrees.
I could check this.
Now, did I make a mistake in my? I clearly was getting tired
No,
towards
you
the
got
end
it
of it.
correct.
No way. Okay.
So I think I see what you did. I didn't convert it to joules.
Now, technically, we could have left it in kilojoules, and it worked. But you saw where I was like forgetting to convert some things because I started getting lazy with my units because I was trying to fit everything on the board. So, for example, like these four, this needs to be converted and that needs to be converted, and then it gets foiled. So, like, there were several places where there was some conversions that needed to be happened. It's best just to make sure we've got all of our units being the same.
I think I like kilojoules.
Do it in kilojoules then.
That's what I'm
Right.
gonna rewrite it again.
You can leave the divide by 1000s in there that I erased, right? So this would be 0.313. This would be 0.037. That would also work out fine.
All right.
It should at least.
Yeah, it makes sense what you did. I think. So you found it in. Actually, wait. I did something.
So, yeah, the important part is the way that we organized our thinking in terms of keeping track of the number of Qs, paying attention to where the energy. Oh, how much of the board is missing? Oh, it's this end. No, it's this whole end is missing. Yikes.
It's been missing the entire.
Sorry, everyone. That's a little better.
So it's missing a small portion of the bottom.
Captions.
Good luck, everyone. Better. Okay. So the important part was, keeping track of our different Qs, what was losing energy, what was gaining energy, identifying which things we didn't know. There was an intermediate step in the middle where I originally was seeing, does all of the ice melt? That same thing we had to do. And I found by doing essentially considering what if the solution went all the way to 0 degrees. I said, oh, if it went all the way to 0 degrees, it would have more energy than needed to melt all the ice. And so it's not going to go to 0 degrees. It's going to go to some final equilibrium temperature. So I ended up with 5 different Qs, 2 of them losing, 3 of them gaining, equal and opposite. Lots to keep track of.
Yes. I think I understand. This was your first step to know that the ice melted.
Yeah, well, I was getting the total amount of energy to make all the ice melt.
Yeah.
And then I compared it to the reaction and solution. And the solution had tons, because this is a lot of mass, right? That's how I had a hunch that it was going to all melt, was because there's a lot of mass here compared to 9 grams, even though it's all the way at negative 60.
Yes, that makes sense. So I'm just writing it all down
No,
still.
take your time. It's also, I also post this stuff to I record it and post it to YouTube. But you can't see the edge of the board, apparently, or the bottom of the board.
You can't see the orange.
Sorry, everybody. Oh, you still can't see the orange.
Yeah, but if you can see the orange, then you can't see the top. Your board's too big for your camera.
No, it's just my angle.
Yeah, because you can just push it back.
Yeah. Oh, yeah, there we go. I'm messing with the wrong thing. I'm just messing with the wrong thing. I'm like, let me change my camera. Just push the board back. Sometimes you overthink problems. And like, I honestly was like, is there a zoom feature in this where I can like make it zoom in and out? And like, I just pushed the board back.
It's been a long day.
I think the part I'm getting a
Been a
little
long weekend.
stuck on is what you were just saying with knowing that all the ice melted.
Right, so that was the intermediate
You
calculation.
compared these.
No, there was a part that I erased. Right, let me
Yes.
see. How's
I
the
feel
other
like-
side looking?
Technically, like, if you had did it without, like, doing the intermediary step, you still would have gone to the same answer. It's just to do it, so, because then, for example, if it hadn't have melted all the ice, then I think the answer wouldn't have helped us, and we would have had to do something else, I think. And
Yeah.
we did that in class. I forgot what you have to do if all the ice doesn't melt, but.
It changes our unknown variables, right? So, let me redraw this picture.
Oh yeah, because then
real
we
quick.
know that the temperature final is
Then you
0.
calculate like a Q remaining, and then
There's a way you can do it with Q remaining.
yeah.
But essentially, let's say this is 0 degrees, right? So our ice system has to warm up from -60 and then melt. And the question is, in my reaction system, it's going to react and cool off. That's too high. Right? It's going to react and then cool off. And if they both end up at 0, we don't know if they just equal 0 or if a portion of the ice melted or if all of the ice or some amount of ice melted. Alternatively, so what I did was I compared these two Qs versus these two Qs. Honestly, this Q alone, this downward, this water cooling off, was enough to do all of this by itself without the chemical reaction. 9 grams of ice would have melted. So at that point, once I realized, oh, all of that melts, that means that there's actually going to be heating up, melting, and then some amount of warming. Whereas this one is going to react and then cool off and not get to 0. There's instead going to be a different T final that we're going to reach.
And you know it because you did the.
Because we did the comparison of the things in black.
And that's what, yeah, we saw that was like the Q of the solution.
Yeah.
It was, I wrote it down.
And I should have, usually when I'm doing this, I just have some weird tape. Usually when I'm doing this, I call this like.
That was the 75 grams of the water.
Yeah.
Times 4.184 times TF, which we're trying to figure out, minus 20. Yeah.
Right? So that Q1 plus Q2 going all the way to 0 would be the maximum of the solution. Whereas this Q1 and Q2, let's call it 3 and 4 so I'm not getting my numbers. Q3 plus Q4, this would be right? That would be the minimum to melt all of the ice. And then I just say which one's bigger. If the max of the solution is bigger than the minimum to melt the ice, I switch to doing the problem that's in orange, where I end up with 5 Qs instead of just 4, because I get this extra bit of heating here. Whereas, if the minimum to melt all the ice is bigger than the maximum of the solution, I have to figure out where I stop along this melting process. Like, I'm going to stop someplace like there, and I'm going to have like less energy. And I have to figure out how much melts, how much doesn't. And we would do a different problem setup for that.
Wouldn't that mean you have 3 Qs instead of 5, not 4? Because you're also removing the Q from the melting of the ice.
No, because you're still going to melt some of it,
Oh, okay.
right?
It's going to end up at 0 degrees.
It's going to end up at 0 degrees.
Yeah, and you know, that's what, there are a bunch of problems like that when they said you calculate the total, you compare that to the energy needed to melt it, you find that difference.
Yeah.
And then you can use that or no, I think then you use the MCAT.
Yeah.
You
Yeah.
have that Q total and you divide that by
Yeah.
added mass to that specific heat.
Yeah.
I think, yeah, that's
Yeah, that works. That works.
at least-
There's a couple different ways to approach it. That's definitely one of them.
Okay.
Other questions about this? I'm going to flip the board back now. I gotta
So
make sure I don't hit the wall.
watched your YouTube.
Oh, okay.
Yeah, Dr. Ziegler puts it in our class.
There are from the pandemic days. There's a couple YouTubes that I recorded for.
These ones
Yeah.
are yours, but like we watch a lot.
Yeah,
From the
yeah.
department.
Okay.
So my question from the homework, so it's just like the metal questions we've done.
From
or
the
Sorry,
quiz?
from the quiz.
Okay.
Is
Is it okay if I erase this and we move on?
Yeah, no,
Cool.
that's totally fine, thank you.
Okay, so let's look at quiz problem 1 and problem 2 and problem 3. Yeah, what's your question?
Okay, so for problem 3, it's like we dropped 94 grams of metal at 79 degrees Celsius into 41 grams of water at 24 degrees Celsius.
Okay. Wait, give me those numbers again.
94 grams of metal, that's 79 degrees Celsius, into 41 grams of water at 24 degrees Celsius.
How many grams of water was that?
41.
41
Thank you so much for your help.
You bet.
And then the final temperature is 33.5 degrees Celsius, and we want to find the specific heat capacity of the metal. So what I did was I didn't plug in any numbers first. I just solved for like the specific heat capacity of the metal first, and then plug in everything.
How did you solve for this specific
So I
capacity?
set up the equation as so like the mass of the metal times the specific heat capacity of the metal times the change in temperature is equal to the mass of the water times the specific heat capacity of water times the change in temperature of the water, and then I just solved for Cm.
Perfect.
And so I got Cm is equal to, so the mass of the water times the specific heat capacity of the water times the change in temperature, T final minus T initial,
Okay.
divided by the mass of the metal times the change in temperature of, oh, sorry, I just gave it to you not on both sides. I just put Cm.
Okay, yeah.
Okay.
I'm just, I have to do it in more steps because I
Okay.
haven't done the problem a bit. Okay, so we've got our metal system. We got our water system. I know the heat capacity for water, so I can just plug that in. Oh, and we know the T final, so we can just plug in the T final here, 33.5. And then we've got our 41, 4.184. And we've got our delta T, which is going to be T finals 33.5 minus 21. And then we got a negative on that side, and you did your rearrange.
Yes. I think it's 24. Sorry.
21 or 24 degrees?
24 degrees.
Okay, 24 degrees. That's the water started at 24?
Yeah.
Okay, this is looking good.
And then I just solved for C.
Yeah.
So, so yeah, I just divided negative 94 times 33.5.
Let's get the delta T real quick. 33.5 minus 79 is, oop, that's not right. 33.5 minus 79. Yes, it's negative 45.5 times negative 94 times 94 negative gets us 4277C. And then we can multiply this all out and see what we get. 41 times 4.184 times quantity 33.5 minus 24. This is 1629.7. Technically, if we wanted to do units correctly, this would be joules, this would be grams Celsius. This is joules. This is grams Celsius, degrees Celsius, times our heat capacity for the metal. We divide over. And divide by 4277. What answer did you get?
I got 0.368.
0.3. I got 381.
Your units are off. The C should be multiplying grams, not divided by.
Wait, what?
Your units on the 4, 2,
Oh, you're right.
are off.
Okay. Thank you.
It won't affect the math, but
No, but it's nice to have the units right. Grams Celsius, so we're dividing, so we get joules per Celsius.
Let me recalculate like where
Okay,
I'm missing.
let's see. Yeah, like your work.
Yeah, where's what I did?
Okay, so we got a 41, 4.184, 33.5 minus 24, 94, 33.5 minus 79. This all looks right. I just got something different than you. Did I make a math mistake or did you?
Well, I mean, my answer's wrong, so. So,
Well,
probably me.
This is why chemistry's great.
this is why math is rough. Both of those numbers make reasonable sense, right?
Mhm.
Because
Yeah,
we
okay,
expect-
so I think maybe I like misadjusted or
Oh
something.
man, this is why multiple choice questions or questions where there's not a good margin, where there's no partial credit, are terrible. Because on an exam where there's partial credit, so it looks like it was just a math mistake, right? Which is really frustrating.
So wait, should this answer be negative or positive?
Heat capacities are not
Oh, it doesn't matter.
negative.
Okay.
It does matter.
Oh.
So heat capacity is the amount of energy to change the temperature of something.
Yeah.
And negative heat capacity would mean something is constantly giving off energy to heat up. Doesn't make sense.
Uranium?
Doesn't make sense. No, that's going through a nuclear reaction to heat up. So there's another chemical reaction there. Negative heat capacities just don't, like, the face you made was perfect because it's just like, it doesn't make sense. Heat capacities should always be positive. They should be greater than 0. Heat capacities much bigger than 4 are kind of absurd, right? Water has one of the highest heat capacities of pure compounds. If you
What
start
does that
making
like,
mixtures and
mean?
solutions.
Like it has, because I think that's something that my second question was question 2, which was the multiple choice one.
Yeah.
Which is, I think, like
This one's hard to do in the
conceptually.
video. So heat capacity is this measure. So here's the way I think about it. I should have asked if I could erase all that, but we figured out we got it right. We're okay. So if we're looking at number 2, and I'm going to do like a little graphic to help us think about what's going on with heat capacity. I'm going to have a beaker with water, and I'm going to have 2 chunks of metal in it. I'm going to have a green chunk of metal, and I'm going to have a blue chunk of metal. And for our purposes, the metals are the same mass. Let's just say they're 10 grams each. 10 grams and 10 grams. The water is going to be heated to, what's your favorite number?
73.
This is going to be at 73 degrees Celsius. Right, so both of those pieces of metal are going to end up at 73 degrees Celsius. Heat capacity tells us how much energy do we need to put into these different pieces of metal to get them to 73 degrees Celsius. Now where that matters is I'm going to have a beaker of water that's at 20 degrees Celsius and another beaker of water that's at 20 degrees Celsius. And I'm going to move this green piece of metal at 73 into here and this blue piece of metal at 73 into here. Which piece of metal, blue or green, is going to move more energy? They're both at 73 degrees Celsius. They're the same temperature. Which one is going to have more joules of energy as it goes?
Whichever has a higher heat capacity.
The higher heat capacity, right? So let's go ahead and put heat capacities on these. Let's say this is 0.38 like we just did. And this other one, let's say it's something high. Let's say it's like 2.1. I don't know what metal that would be. That'd be something crazy. But this means, looking at the units, right? This is joules of energy put in to raise a gram of material by a degree Celsius.
So like in the end, if they're both at 73 degrees Celsius and then they like are in that water, would the water not reach the same, or the water and the metal, like at some point in time they both reach the same equilibrium? Like
These
temperature?
two separate ones?
Yeah, like would they, or does the heat capacity
I
make it
mean-
so they don't?
Heat capacity makes it so they don't unless we rate, like, as long as they're isolated. If they're open to the same room, of course, eventually. But if they're isolated in really nice coffee cups, sealed up really well, this
They
will
won't
not
reach the same temperature.
they're not going to reach the same temperature. So what heat capacity means here is if I want to get this piece of metal from up to this temperature, I need to put in 0.38 joules of energy for each gram for each degree Celsius.
So that means that one would heat up the water more than the
It
other
would
one?
take, well,
Or
it
it
would
takes
take
less
less
energy.
energy to get this one to 73.
Uh-huh.
This one, I need 2.1 joules of energy for every gram, every degree Celsius. So I would do 73 times 2.1 times, or sorry, 73 times 10 times one of these two to figure out how much energy is embodied in each.
Okay, so each of them have a different amount of energy in them.
Yeah. Now I move them. Which one has more energy as I move it?
The one with more heat capacity.
The one with more heat capacity. This one's going to be moving like a lot. I should have made this point too, so it's just like 10 times. It's going to be moving about 5 times more energy. 5 times more joules of energy. So as I move those two things over, this one's going to have 5 times more energy. So this temperature is going to end up going higher as it loses its energy to the water.
Because more of its energy can be lost to the water?
Yeah, so after I move it to this new container, I move both of them to new containers, they're both going to lose energy to equilibrium, right? They're going to reach equilibrium. But this one is going to have less energy to put into the water because it took less energy.
Okay.
This one's going to end up at a higher temperature because it took more energy with it. So heat capacity is like a energy carrying capacity.
And the way it like relates to heat is not that it's heated at that, it's just because it takes that much energy. And so, okay.
Yes.
I think because I was associating it with heat, so that's why I was getting confused.
It's capacity. It's like how big's your suitcase?
Can I assume that for a good example for how this would work is basically saying because the grams are the same, you can get rid of the grams in it, so it's joules per Celsius?
Pretty much, since it's the same grams. Yeah. That would work.
Thank you.
You bet. Okay.
Get to class.
I have to figure out what I'm doing for my next class. I do have office hours tomorrow as well.